This is section 4.5. We are going to simplify radicals and solve radical equations by finding their square roots. First of all, let's write down some definitions. Given any r squared equals s, then r would be positive square root s, and r could be negative square root s. A lot of the time we will write the solution as plus or minus the square root of s. I'll show you that more as we get into the equations. The expression square root s, that whole thing is called a radical. Just the symbol itself is called a radical sign. A lot of times you'll say square root. And the s, or the number inside the radical sign, is called a radicand. There are two properties that are very important to know in order to simplify radicals. First, if you have the square root of a times b, you can split that up into the square root of a times the square root of b. And the same thing can work for quotient property. If you have the square root of a fraction, you can split that fraction up into two square roots. Also, when simplifying, a radical is simplified if there's no radicand that has a perfect square factor other than 1, and there is no radical in the denominator. So let's simplify. First of all, we have the square root of 196. Now, if you remember, square root means what number times what number would give you this number answer. If you think about 14 times 14, that's 196. So the square root of 196 is 14. So that would be the simplified form of square root 196. Now, square root 45 is not a nice, pretty number. It's going to be a decimal. So we're going to keep this still in radical form, but we're going to simplify it. So we've got to find perfect squares that go into 45. Now, you may want to write these down somewhere. Remember, the perfect squares are 1, 4, 9, 16, 25, 36, 49, 64, 81, 100, and we could go on, 121, 144. Those are perfect squares because 1 times 1 is 1, 2 times 2 is 4, 3 times 3 is 9, and so on. Like 36 is 6 times 6, so the square root of 36 would be 6. So let's go back to 45. Which of these perfect squares, what is the biggest perfect square that goes into 45? Looking at those numbers, I would say 9. So I'm going to rewrite this as the square root of 9 times 5. And this is where the product property comes in. I could rewrite this as the square root of 9 times the square root of 5. And you may start to get into the habit of just writing this as two square roots right from the beginning. So it's square root 9 times square root 5 for the square root of 45. Now, the square root of 9 is 3. So I'm just going to rewrite square root 9 as 3, but then I have the square root of 5 left. So that would be the simplified form of that radical. There are no other perfect squares other than 1 that goes into 5. So that is simplified. Square root 6 times square root 8. When you have those multiplied together, I would first put those together using the product property. I would take 6 times 8, so it would be the square root of 48. Now think about your perfect squares again. What's the biggest perfect square that goes into 48? If you go through that list, you'll find out that it's 16. So I'm going to rewrite the square root of 48 as the square root of 16 times the square root of 3. 16 times 3 is 48. So now if I'm going to simplify that, the square root of 16 is 4, and the square root of 3 is left over. You just bring that down. So that would be the simplified form of that radical. Moving down to this fraction, when you think about the product property we talked about, you could rewrite this as the square root of 16 over the square root of 25. Can you take both of those square roots? You can, because they're both perfect squares. Square root of 16 is 4, square root of 25 is 5, so that's as simplified as we can get for that radical. Square root 25 over square root 3. This one's a little bit different. Square root of 25 over square root 3. I know the square root of 25 is 5. Always simplify as much as you can with these first to begin with. Square root of 3 I cannot simplify. But if you go back to the definition of when things are simplified, it said that you cannot have a radical in the denominator. Here's how we get rid of those radicals in the denominator. When it's just a square root, the nice thing is all I would need to do is multiply this bottom by the square root of 3, and that'll get rid of the radical. But remember, when we're doing a fraction, if I want to simplify it, that means I also need to multiply the top by the square root of 3. So now when I do this multiplication, on the top I've got 5 square root 3 over square root 3 times square root 3. If I put those together, that would be the square root of 9. What's the square root of 9? Square root of 9 would be 3. So that simplifies to be 3 in the denominator. Another way to look at this is whenever you have the square root of a number times the square root of the same number, it's just that number without the square root. Okay, so you put those two together, square root of 9 would be 3. So that would be the simplified form of this radical. This one gets really weird because we have a radical in the denominator. However, everything is simplified to this point, except we have to take care of this radical down here. What we're going to do is multiply the top and the bottom by something we call the conjugate. Okay, the conjugate is when you change the middle sign. So I'm going to multiply this by 2 plus the square root of 3. When we do that to the bottom, we also need to do that to the top. Because then it's really like multiplying by 1, and when you multiply by 1, you're not actually changing the value of this number or fraction. Now I'm going to multiply this out. This would be distributive property. 3 times 2 is 6, plus 3 times square root 3. I'm just going to rewrite that as 3 square root 3. Over, now we're going to FOIL. 2 times 2 is 4. Now the reason why we multiply by the complex conjugate, actually it's not the complex, it's just the conjugate. The reason why we do that is what's going to happen to the outside and the inside. Here I have positive 2 square root 3, and inside I'm going to have negative 2 square root 3. The cool thing about that is that those cancel each other out. Okay? For now I'm going to write this out so you'll see. It'd be plus 2 square root 3 minus 2 square root 3. And then when I take negative times a positive, that's going to be negative. And we just talked about square root 3 times square root 3 is just 3. Now when I simplify this, I'm going to have 6 plus 3 square root 3 over, these are going to cancel each other out. 4 minus 3 is 1. One other way to write this would be 6 plus 3 square root 3. Because when you have something over 1, you don't have to write the over 1. So that would be the simplified form of that fraction. No radicals in the denominator. Now we're going to solve some equations using square roots. These instructions are in your notes, so you can take a look at those anytime you want. Let's do some examples. I want to get this x by itself. So the first step would be to add 6, just like we normally would with any equation. So I'd have 4x squared equals 48. Now I would divide by 4. So I end up with, those factor out, x squared equals 12. Now here's where we have to, in order to get the x by itself, I would have to take the square root of both sides. And we talked about at the very beginning when we did some definitions, when you have a variable squared equals a number, whenever you have to put this square root on here yourself, you actually have two answers. You have a positive answer and you have a negative answer. And for this, it's going to be plus or minus 12. Okay? The square root of x squared, square root and squared cancel each other out, so I'm left with x. That's why we took the square root. Now, your answer is going to be the positive and negative of square root 12. The only thing we need to do here at the end is to simplify the square root of 12. I can write 12, if I find my greatest perfect square that goes into it, would be 4. So it would be the square root of 4 times the square root of 3. That would still be square root 12. So when I write my final answer, keeping that plus or minus out front, the square root of 4 is 2 and square root 3 is left. So x equals positive 2 square root 3 and negative 2 square root 3. This next one's a little bit different because you have a binomial squared. I'm going to try to get this by itself first. Now remember, we could divide by a half to get rid of this 1/2, or that is the same as multiplying by the reciprocal of 2. Here those would factor out. That leaves us with x plus 8 squared equals 28. Now, in order to get rid of the squared, since I have something squared, to get rid of the squared, I would take the square root of both sides. When I do that, over on the left, the square root and the squared cancel each other out, so I'd have x plus 8 equals, now here's where you have to be careful. Whenever you put this square root in, this side over here that doesn't have the x, you have to put plus or minus in front. Now we do the square root of 28. The greatest perfect square that goes into 28 would be 4, and that would be 4 times 7. Okay, so I've got x plus 8 equals plus or minus, the square root of 4 is 2, square root 7 is left. Now I still need to solve for x by subtracting 8. So I'm going to subtract 8 from both sides. That leaves me with x equals, these are gone. Now be careful how you write this. Okay, I'm going to keep the plus or minus 2 square root 7. I'm actually going to put this negative 8 in front, only because it's less confusing in the end. So it's negative 8, then I put the plus or minus 2 square root 7. So I've got two answers. I've got negative 8 plus 2 square root 7, or I have negative 8 minus 2 square root 7. So that would be my solutions for this problem. Now, just to throw in a little extra something, if I ever had an answer of x equals 3 plus or minus 4, if you get something like that, you can actually work those out. So think about 3 plus 4 would be 7. 3 minus 4 would be negative 1. So that would be your final answer if you ever got something like this for your answer, where you don't have any square roots. Go ahead and work out those constants. And that's going to conclude section 4.5.